So, just opened RADAN. You should now see RADAN 7 on my screen here. And we are going to get started with some processing. So, like I said before, when you first open RADAN, you should see a window similar to this. You may or may not see all of these ribbon options up here, but as long as you have everything from home to 2D interactive, as well as the Google Earth ribbon, you should be in good shape for today. If you don't see anything on the right-hand side, as you might have noticed, I clicked on Global Settings up here in the Other Windows area to get this to appear. So please click on that to get the right-hand ribbon to show. This is always a great place to start for RADAN, telling RADAN where our files that we want to process are located. So we're going to head over here to the Global Settings pane. We're going to go over here to the source directory. And I'd like you to double click on the term source directory. When you double click on it, a file browser will show up on your screen. And where I'd like you to go next is the location containing the RADAN class datasets. I want you to go to where you have that data saved. Mine is right on my desktop. Yours might be in a downloads folder. It may also be zipped. So if you haven't extracted the files from the zip folder yet, I would recommend doing so before continuing. You can just go to your downloads folder. If you right click on the folder, you might see a zipper on it, and you can select extract all to extract the files from there. And then you're going to want to highlight the non-zipped folder for your source directory. So again, mine's on my desktop. I have a RADAN class datasets folder here. You should have 3 folders inside of it. One of them cemeteries, one of them grids and GPS, and the last GSSI sample data. We're going to be in this sample data folder for the day. So double click on that to highlight it. We don't need to highlight any of these other folders here at this time. We might work in 1 or 2 of them later on today, but the files that we want to work with are just sitting in this folder here. So all we need to do is highlight GSSI sample data modified. Don't worry about clicking on any of these others. This should be highlighted in blue, and then we can click OK. Now, like I specified earlier, if you want to name your files yourself, you can specify autosave files to no instead of yes. I'm going to leave mine set to yes for now. If you set it to no, you will have the option to update your output directory as well. So feel free to update your output directory as well before continuing. Okay, so again, this side panel here is the Global Settings Other window. So if you click on the Home ribbon and you click on Global Settings, this pane will appear and disappear. So just make sure that this is highlighted in orange, and then you should see it over on the side. And then we're updating our source directory to the RADAN class datasets folder, and then inside there, the GSSI sample data folder. And then we're clicking OK. Nothing else in here needs to be changed at this time. These are all OK the way that they are. We will be changing our units tomorrow when we're assembling 3D grids. But at this time, it really doesn't matter what this says here. This could be in really any units. Once we get the file open, we can always head to the View ribbon and change our units from feet to meters to miles to centimeters to whatever unit you want, horizontally or vertically. But for now, we can just leave these set to the default. We don't need to worry about any of these options here. Up here, we also don't need to worry about any of these options. These will come into play later on in some of the processes we'll do next. But for now, default options are fine. It's really just the source directory we need to be concerned with. You'll see for the most part, we don't have any data open. We've just told RADAN where to look, and for the most part, everything else is grayed out. We can make some adjustments to color tables, color X forms. I'll talk about that later, but everything else is grayed out because all of these are specific for the data that we see on the screen. Of the few things that aren't grayed out, there is global settings, there is open, and there is help. To discuss help very briefly, the help button gives you the ability to view the index. The index is actually the RADAN 7 manual. If you want to try clicking on that now, you'll see a PDF of the manual will pop open, giving you access to the whole manual to find out a little bit more info about specific processes or to walk through some data processing tutorials. So we do have some tutorials written into the manual. A lot of what we're going to do today is actually specified in section 5 of that manual. We're just going to go into a lot more detail than the manual specifies. There's also about just tells you what version of the software you're running, copyright information. You can also update RADAN through this button and view changes to previous versions in the update notes. So update notes is basically release notes, what's changed in successive versions of the software. And the update button will check our servers and see if there's an update available. If there is, it'll walk you through how to perform the update. Updates are always free, so it would be worth checking this every so often just to see if we have a new update out. Okay, so far we've updated our source directory, and that's pretty much it. So let's start opening and processing some data. We're going to head over to Home. We're going to click on Open. It's going to open the sample data folder. We can see all of those other folders as well as DZT files. These are the raw GPR data files we were looking at earlier, the DZT files containing all of the two-way travel time and amplitude information we collected out in the field. The first file we're going to open today is a file called Strats. So please double-click on this file or click on it once and click on Open. And the Strats file will then show up on your screen. A couple of things happened here. We double-clicked on this file. It's now visible on our screen. A lot of the options at the top of the screen, which were previously grayed out, are now available. We will talk about most of these over the course of class the next couple of days, but just to touch on a couple of them right off the bat, if you click on your data once and click and drag and move your mouse around, you'll see that you have a crosshair that moves around through your file. As we discussed earlier, right, this file is just like looking at data on your SUR 4000 or your Mini XT or your utility scan, where we have horizontal distance traveled running along the horizontal axis, and we have depth, or really two-way travel time on the vertical scale. So we have depth and we have horizontal distance traveled. This is our viewpoint here. As you move your mouse around over the file, if you're paying close attention to the bottom of your ribbon, you'll see the file name, Strats.DZT. You'll see a distance, DIST, equals some number of feet, which is the horizontal distance from 0 to the maximum distance traveled where your mouse is currently located. We also get a scan number. So you get the scan number that your mouse is currently over. And lastly, a Z value. Z is depth, how deep the horizontal cursor currently is down the screen. So again, I'm clicking and dragging, I'm looking at that crosshair, and that horizontal line, the Z value specifies where that horizontal line is. So this allows you to open a file and quickly get a sense of how far into the file a target or feature is and roughly how deep we think that target or feature is. Important to remember that the depth is only as accurate as the dielectric constant. So assuming we did our due diligence out in the field, we may have already calibrated the constant to a fairly representative number, or we may not have. We may just have a test value in there, right? So what if we have some questions about how this file was collected? Well, we can view all of that information in the Other Windows area, right? You'll see global settings is currently grayed out. We can't do anything in there with a file open. But now that we have a file open, we can take a look at the file header. The file header is something that I make use of as one that often receives data that I did not collect. If you're looking at a file that you collected a while ago, or you're looking at a file that a colleague collected, you can click on the file header to see when this file was made and the parameters that were used when it was collected. I can see that this was created in 2002. It was collected at 64 scans per second, 3 scans per foot, 512 samples per scan with a dielectric constant of 25. I can see that it was set to a range of 100 nanoseconds, which corresponds to a depth of 32.8 feet. And that the antenna type is currently set to 400D, which is a very old model number for a 400 megahertz antenna. A lot of the other information in here is zeroed out because it has an older file header that doesn't have quite as much information in it as our newer systems have. If you're opening very recent data, you'll also see your serial number, the antenna serial number, and a whole bunch of additional information. But apart from all this, we can also see what processing's been done to this. This is SUR 3000 base data, which means the processes have been saved into the raw file. Actually, this might even be SUR 20 data. So we can see the range gain, we can see the time variable gain, as well as some filtering that's been done to it. We will break down these filters later on in the day. So if these filter names and these processes don't make a whole lot of sense at this time, don't worry about it. We will talk about all of these processes in detail later on today. But this gives us a good summary of the file where we know what's been done to it already, so that that can help guide maybe what we might want to do next. All right. So we've looked at the file header. We can close it if we're done with it. And now let's talk about the colors we're seeing on the screen. I can see some colors here. The file looks pretty good, in my opinion. It might look different from how yours does. So let's talk about what's going on there. Well, I'm using a different color table and maybe even a different color transform than what you may be using. Let's start with the color tables. When I click on color tables, I'll see that there are 30 options for me to choose from. And as I highlight over each one, I can see that the file will look different. It might be helpful to visualize a scan bouncing to the left and to the right from some central location, where the center is the very center of this color table here. And anything that goes off to the left is a negative amplitude reflection, and anything to the right, a positive amplitude reflection. The color table is simply representing what color corresponds to positive and negative. The default is color table 17, which is this true gray table. Anything off on the left, a negative amplitude, is colored black. Anything off to the right, a positive amplitude, is colored white. I prefer this out in the field. When I'm collecting data, I use grayscale all the time. When I'm in RADAN, the story is different. When I'm in RADAN, I tend to stick with these more colorful tables, not necessarily the rainbow ones. I think the rainbow ones have a time and place, but that time and place is usually not for 2D data collection, as it's generally hard to figure out what's negative and positive if you use one of the rainbow tables. I tend to prefer these colorful tables, but they go from one color to one other color. If you like grayscale a lot, I would recommend trying 18 out, especially for some of these processes we're going to do later on. Sticking with grayscale, while great for in the field data collection, it tends to make some of the later processes we'll do more difficult to perform. And the reason for that is usually that the tool that we use for the process ends up, if you stick with the grayscale table, the tool itself is also gray. So the tool becomes difficult to see and difficult to make adjustments to. If you stick with any other table, the tool is a lot easier to see and it's a lot easier to work with. So I would recommend, to make processing easier and to make the tools easier to use, sticking with a non-gray table. If you like grayscale, which I do myself, I would recommend giving 18 a shot. It's very similar. It's just brown instead of gray in the middle. And the tool is going to be a lot easier to see. Tools that we'll use later on for processes we'll do in the afternoon. I also like to use other tables like 20, 22. 22 is my personal favorite. No particular reason. I just like this shade of blue. But you can stick with any one you'd like. These like upper, lower 20s are really good as well, going from one color to one other color. All of these would be really great choices for RADAN. I would not recommend 29 or 30 for right now. I really like 30 for 3D grids, but again, it's a little too complicated for analyzing 2D data. So I usually don't look at my data in 2D using this table. But for 3D grids, it's actually pretty cool. So I'd recommend start with 18 as a color table, or 22, 23, 24. Those are all really good for a lot of the processes we'll do later on today. Regardless of what color table you're choosing, I have a strong suggestion for your color X form. The default color X form is 3, which is fine most of the time. So look at the color X forms and take note of what's changing when we choose different color transforms. The colors themselves are the same, but the color that corresponds to a strong negative or strong positive amplitude reflection changes. For linear, targets will be very black or very white if they are very strong. For exponential, which is color transform 1, targets don't need to be that bright. They don't need to have a particularly strong amplitude, positive or negative, to show up very white or black. And we can see that on the screen. That is the case. Very weak reflections are very bright and easy to see with the exponential color transform. 3 is a fine default, but I find myself using these LM tables a little bit more often. If you look at the LM tables, you'll see that the LM tables just make smaller amplitude targets a little bit brighter than the linear table would normally do. Linear is very similar to LM18, so I generally don't use LM18, but if I'm collecting data in soils, of which this is the case, LM12 and LM8 tend to be really good choices. I'm on LM8 right now, and I really like it. I'm probably going to stick with it for this file. If you're doing concrete analysis, LM8 and LM4 are really good choices. This is also the case for road scan and bridge scan, so pavement thickness analysis or bridge deck deterioration analysis. LM4 is the best color table for that, in my opinion. But for concrete, I would say LM4 or LM8 are generally pretty good. For soils, LM8 and LM12 tend to be pretty good. I'm going to stick with LM8 for right now. It's making my targets a little bit... Oh, I think I jumped over to LM4. It makes the targets a little bit brighter and easier to see without overdoing it. So think of these color transforms as a different way of adding screen contrast or a different way of adding gain. It can sometimes completely negate the need for adding more gain just by picking a specific color transform. The ultimate goal of both methods is to make your targets brighter and easier to see. And sometimes you can do all you need with just a different color transform. And then display gain, just for full measure, display gain is another way of adding screen contrast. The bigger the positive number is, the brighter everything will be. The bigger the negative number is, the dimmer everything will be. You can also plug in a custom value, not here, but by right-clicking on your file. You can go over to display gain and then specify a custom positive or negative amplitude. So again, right-click, display gain. You can specify a custom value to brighten or weaken your image accordingly. I usually don't do display gain at this point unless if I really need to. Usually I can get away with a different color transform doing the brightness adjustments I would want to do. But if you need a little bit of an extra kick, sometimes an extra 3 decibels or 6 decibels of gain can do the trick. Okay. So far, we've really just changed our source directory and opened and looked at a file. And we're just making small adjustments to the color table and color transform to get ready for the actual processes we want to do. So let's get into that. If you go up to the top ribbon, you'll see we have Home, View, Easy Processing, and Processing. We're going to head over to Processing. When you click on the processing pane, you will see all of the processes you can do in RADAN. If you're newer to GPR or newer to data processing, you may have tried easy processing first if you were processing data beforehand. You'll see easy processing has a number of processes all in an order. These processes are exactly the same as the processes you see over here. They're just placed in the order that you usually do them in. We are not going to spend any time here over this class, but if you ever need a quick refresher on what order you usually do processes in, this might not be a bad thing to just take a look at. I don't usually like to describe processing as a cookie cutter process because it really isn't. Every site's different and the processes you want to do are going to be different depending on what you want to get out of it. But for a fair amount of processing, you may find yourself doing the same thing over and over again. And easy processing has the most commonly used steps in the order that you would do them in. But over the course of this class, we are going to stay in the processing pane. So we've opened a file, we've changed the color, and now we're ready to process it. The first process we're going to take a look at is a process right in the middle called horizontal scaling. If you click on this process, you'll see that a pane opens up on the left-hand side of the screen. This pane is the processing pane. It will look different when you have different processes selected. Horizontal scaling has a pretty straightforward processing pane. Sometimes you'll see some information up here. Currently it's grayed out, but other processes might have a waveform or might have a velocity plot up here. So we'll take a look at those when we get to those processes. But for a few of these, especially the first ones we're going to do, they're going to be grayed out up here. So nothing to see up here. It's just 3 buttons, OK, cancel, and apply, and the properties we might want to change down below, of which there are 2. Let's start with the 3 buttons up here. If you have everything set the way that you want and you're ready to run this process on the file and you want to open it as a newly processed file, you can make your adjustments and hit OK. That will run this process, fully process the image, and open a newly processed file, which will show up right next to the Strats tab up at the top. If you're making some adjustments and you're not sure what you want yet, you can hit the Apply button. The Apply button will show you what this does on whatever data you currently have on the screen, giving you the option to view it and think, is that what I want? Do I want to make some more adjustments? And then you would either hit Reset, Apply turns into Reset after you click it, or OK, which is the button you'd press when you know that's what you want and you want to actually run this as a new file. The last button is Cancel. You would hit Cancel if you don't want to do this process. Maybe you clicked on it accidentally, or you tried some values and you're like, this isn't the time for it. I want to do something else first. You can hit Cancel, which will close this pane and give you the option to select a different process. So that's what these 3 buttons do. Now let's talk about what the properties themselves are. Horizontal scaling is a process that gives you 3 different operations: stacking, skipping, and stretching. This process allows you to shorten your file by some number of scans or stretch out your file by some number of scans. The way that you shorten the file, you can either stack or average those scans together or skip them, which means you toss them completely out. Both methods will ultimately shorten your file, but the way that they shorten it will differ. You're either going to average out those scans or skip them, toss them out completely. Stretching is what you would use when you want to stretch out targets and features. Similar to the zoom option on your utility scan or SUR 3000, or sorry, utility scan SUR 4000 or structure scan mini XT. The zoom feature is very much what the stretching operation does here, where you can stretch your file by some number of scans. A helpful trick for these processing panes, the ones especially that are more complex, is you can always click on these options here, and RADAN will give you a brief rundown of what they mean below. Sometimes these panes can be less helpful, just says what the operations are, but sometimes they can be very helpful. They can tell you that if you type in a number and you pick stretch or skip or stack, this is what the number will do. So I often, take a look at this just for a quick reminder on what these processes do, and I'd recommend you do the same. There are a lot of properties in here, and it can be hard to remember what all of them do. So if you want a quick reminder on what they do, just try clicking on this and see if you get some information down here. You can adjust the size of this by moving your mouse by this bar here. You'll see that my cursor goes from a normal cursor to a double arrowed cursor. And now I can click and drag on it to give myself more space on the screen. Okay, so now we've talked about what this process, how this process works, but when would I want to use this? Horizontal scaling is a good process to use when you want to exaggerate or when you want to exaggerate features. So this is what stacking would be used for, or when you want to truncate a file that's much longer than you need. So one application that I see this used often is in bathymetry surveys, where you're taking an antenna and you're locating the bottom of a lake bed or a riverbed, and you're collecting data in time mode. So you're just transmitting maybe 20 to 30 scans per second. You have it sitting in a raft, and you're just moving at a fairly consistent but slow pace over the river or lake bed. You're transmitting and receiving and getting a reflection off the bottom, but you'll likely end up with a very, very long file. You can look at that whole file and, scroll through it to get a general sense of where your lake bed bottom is and how the depth changes over distance traveled. But you can also stack or skip some scans to make the file a lot smaller so that it takes up just one screen's worth, giving you a nice representation of the bottom or a rough idea of how the bottom changes on one screen rather than having to scroll through the whole file. So that's like the one time that I've really seen this process used a lot has been in that specific application, but you may find uses for this elsewhere. Anytime you need to exaggerate features or shorten features, this can be a good process to apply. Let's see what it actually does. So I'm going to start by stacking, and I'm just going to stack this by, we'll say, 2 scans, right? So that will half the size of this file, stacked by 1 over n, where n is the number of scans. So 1 over 2, that means this is going to stack every 2 scans together, giving me a file that's half the size that it is currently. You can hit apply to see how it looks, and then you can hit OK to actually run the change. Couple of things you might notice when you hit apply. If you look at this file here, you'll see that it's a little over 350 feet long. When I hit apply, it now looks like it's a little over 150 feet long. It's not actually the case. The horizontal scale just hasn't updated yet. You'll often see some display issues when you hit the apply button where it does some things right, but it doesn't do everything right. So don't be alarmed that this looks like it's actually cutting off half the data. It is, but when I hit the OK button, you'll see that the horizontal scale will still be accurate to a little over 350 feet. But the file has definitely been compressed. We've stacked some scans together, making the features a little bit, change a little bit quicker, we'll say. If you want to try another horizontal scaling process, you'll see that we have 2 tabs now. I have a Strats P_8 and I have a Strats file. Yours likely says Strats P_1. I've done a few processes to Strats, so I have a lot of processed versions of it. But if this is the first time you've processed Strats and you have autosave files set to yes, this will say Strats P_1. I'm going to click on Strats again. I'm going to head over to processing. I'm going to head over to horizontal scaling, and we can try one of the other operations like skipping or stretching. All of these processes will work fairly well. You will notice if you try the stretching process and you hit the OK button, your file is going to look very, very bright. We currently have a bug in this version of RADAN for just the stretching horizontal scaling process, where your file will look very, very bright afterwards. This is fixable with a process that I'll show later on. So don't be alarmed if you find that you need to do this and you have this display issue afterwards. This is very easily fixable using one of these FIR or IIR filters. Again, I will explain this later on. I don't want to do it quite yet because it's going to open up a big can of worms, but we will talk about these processes, and these are the processes you'll want to do after horizontal scaling stretching when you see this very bright image after the fact. But if you just want to take note of that at this time so that you have it, after you see that, one of these filters will, either one, it really doesn't matter. I will make a strong case for using the IIR filter only, but one of these 2 is perfectly fine to fix it afterwards. It's a pretty straightforward process. You try pressing in try some different numbers, and your file will stretch or skip by some amount. That's really all there is to say about scaling. But let's say you find yourself in the scenario that was just described. You collected a file, and even though it says 350 feet, you know it was 370 feet. Or maybe you collected a file and you didn't even have a survey wheel. Whether it was broken or you were collecting data over water or over ice and you couldn't reliably use a survey wheel to keep track of distance traveled. In all of those cases, you can use a process to help normalize your distance and get your horizontal distance to rectify itself. So let's talk about how to do that. The first thing I'm going to do is close the files that I currently have open. You don't necessarily need to, but in practice, I usually just close out my files when I'm done with them. We will go back to Strats later on, but for now, I'd recommend just clicking the X next to the tab over on Strats. Closes it. Click on the X's next to the other tabs as well to close all of them. And then you should see a screen like this here. All right. And then we're going to go back to Home. We're going to click on Open. And this time, we're going to open the file called DistNorm. All right. So when you double click on the DistNorm file, you will see a file that opens up here. I'm going to do something very quickly to get my file to look the way that yours does. You're going to see a file that looks like this with a number of vertical dashed lines going down the screen. Now, your dashed lines may or may not look like mine. They're either going to go all the way from the top or bottom, or they might only take up the first like 10% of the screen. To affect how these vertical dashed lines look, these vertical dashed lines are called user marks. They're placed by pressing the mark button on your control unit when you're collecting a file. The mark button's not used all that much anymore, but back when GPR was first used, survey wheels were not really a thing, at least for the first couple of decades. So the only real way we could get a sense of distance traveled is by transmitting scans per second and by using physical indications of when we've moved 5, 10, 15 feet across the floor. And every time we drag the antenna past one of those physical markers, we would place a user mark in the file, which would put a vertical dashed line through, allowing us to look at the file after it's been collected and say, okay, between these vertical dashed lines, I know I have roughly 5 feet of movement. Again, not used all that much anymore, but it's still used in situations where you may not have a reliable survey wheel use. This could be for lake bed surveys. This could be for ice surveys as well, where you're just transmitting scans per second and then trying to get a sense of horizontal distance traveled using GPS or using this distance normalization process. So I have these vertical dashed lines here. I can affect the way that they look by looking at the window settings other window. So if you have Home, the Home ribbon highlighted, underneath the file header, you have a window called Window Settings. Window Settings opens up over here, and among other things, you have access to the marker style. And there are 3 options here: none, short, and long. None will hide your marks, definitely not what we want in this case. Short will show them on the screen, but they don't take up the whole screen's width. They're just small dashed lines at the top. You might prefer this. I prefer long user marks. They're a little easier for me to see. And if you also prefer this, but they don't quite look like that, please head over here and switch your marker style to long. As long as you can see them, feel free to leave it set to short or long. It does not matter for what we're going to do next. You just need to be able to know where they are. So I have some user marks on the screen here, and I will tell you a little bit about this survey. This survey, I'm going to close Windows settings so that it's gone too. This survey was done without a survey wheel in time mode. And user marks were placed at some consistent distance. Every 5 meters, we placed a user mark. What you can do with this file after it's been collected is tell RADAN, in between these marks, I have 5 meters worth of movement, and I want my file to have some number of scans per meter. In our case here, we wanted to have 25 scans per meter. RADAN will add or remove scans to make that true. We do need a consistent scans per unit value to get this to work. But RADAN can add or remove scans to get this accurate. So we need to tell RADAN how far apart each mark is, and we need to tell RADAN what we want our scan density to be, how many scans per meter or how many scans per foot we want. But the first thing we need to do is take care of some issues in the file. So if you've ever collected data with the antenna just sitting on top of the surface and having it constantly transmit, this image, at least for the first 5 meters, might look a little familiar, where you just have consistent horizontal lines on the screen. But in the middle of that, we do have this user mark here. This user mark was placed accidentally. And if we were to keep it here and apply our distance normalization, it would actually mess up the horizontal scale because it thinks we've moved from this user mark to this next user mark, when in reality we haven't. We haven't actually moved the antenna yet until we hit the second user mark rather, that's about 5 meters into the file. So what do we do when we have a user mark that we no longer need? Well, there are 2 ways to get rid of this. There's the very fine hand motion movement where if you can get your vertical line right over top of the user mark, you can right click on it, you can add/edit your waypoint, and if you're lucky, you'll see a check mark here that you can click and then hit OK. And when you hit OK, your user mark will go away, and now we can continue with the DistNorm process. That takes a very careful hand, and it might take a couple of checks to actually get it right. I'm going to put my user mark back, and I'm going to show you a more reliable way. And the way that I'd recommend you do it is using the table's other window instead. The table's other window is an often overlooked but really helpful window. It gives you tables of information. You can click on different tabs down here to view different aspects of this file. The default, which is waypoints, is where we want to be. With the waypoints tab selected, you can click by this file. You don't need to be right on top of it, just sort of click around it, and you should see under, yours is going to be scan 50, mine's 49. I see a check mark here where the user mark is. I can then click on that check mark. It'll go away. And now we're okay to continue. The waypoints table is also where you can make adjustments to the distance traveled in your file. If you know that you collected some other distance, you can actually head up here, double click on this distance, and type in what the new distance is. And it will change the horizontal scale accordingly. If you know you moved 370 instead of 350, you can just type in what your new max distance is, and it will adjust the scans per foot accordingly. Or scans per meter in this case. In our case, we don't want to do that just yet. But that is a quick and easy way to fix your horizontal scale if you find that the survey wheel did not measure the horizontal distance accurately. What I'd recommend if you're going to start making changes in here is saving a copy of the file that you can make adjustments to, so that you don't overwrite any of the information in here that you might be erasing and replacing.
Thank you.
Best done by clicking on the main button and then just clicking Save As RADAN File. This will save this as a new file. You can give it its own name, and then you can start making adjustments to the waypoints table or to other parameters without worrying about overwriting the raw file. Okay, so we've gotten rid of the extra user mark, and now we're ready to normalize our horizontal scale. So fortunately, when the user collected this, they wrote in the notes table what they were interested in. They wanted 25 scans per meter and 5 meters in each mark. So 5 meters between each user mark. With that information in mind, we can then go over to processing and to the distance normalization process, right under horizontal scaling. You'll see that, again, we don't have anything up here. We don't even have an apply button. It's just OK or cancel. And we have 3 options down here. We're going to need to change all 3. Scans per unit should be set to 25. Units per mark, that's the distance between each user mark, should be set to 5 meters. And apply to user marks, we want to set that to yes. So this means we want to use the user marks on the file. We want there to be 25 scans per meter and 5 meters between each mark. We can hit the OK button. The process will run over our file, and we'll now have a new file with a fixed horizontal scale. Now, as I'm sure you've noticed, your file may have also done what my file did. You might have these vertical bars on your file now. This is another display issue that we're hoping to fix in RADAN. That's fixable with the same filter, FIR or IAR filtering. So if you run this process, you see these bars on the screen and you want to filter them out, you can get rid of it with a quick IIR or FIR filter, which again, I will show you later on today. But a lot of these weird display issues can be fixed with one of these filters that you apply after running the process. So we're going to get started up again with some new material. To recap what we've done so far, so we started off the morning by discussing some foundational GPR theory, breaking down why the image looks the way that it does and what exactly we're collecting. There's 2 crucial pieces of information: two-way travel time and amplitude, which are displayed on the screen, converted time into depth using the dielectric constant, and the colors on the screen representative of the amplitudes, whether they're negative or positive, what negative and positive amplitudes mean, and how strong the reflections are by how bright the colors are on each extreme. The colors, of course, corresponding to the color table and even the color transform you might be using when you're viewing your data. To recap further on that, I'm using color table 18, and for strats, at the very least, the file that we're looking at here, I'm using color transform, what number is that? Color transform 8, which is also LM8. I would strongly recommend for soil data, I tend to stick with LM18, 12, or 8. Usually 12 or 8 are the 2 that I fluctuate between, but sometimes LM18 hits the spot. And then for concrete data, LM8 or LM4 tend to be pretty good. More so LM4, but Could be either one. Again, it depends on, what you have set in your raw data, what the raw amplitude is. We talked about two processes so far. We opened up the strats file and we took a look at horizontal scaling, a process that allows us to stretch or compress the file, as well as a process called distance normalization, which we can use to fix the horizontal scale on files collected without a survey wheel. And we also talked about ways to fix the horizontal scale, whether or not you used a survey wheel after the fact in the file header. All right. So for our last horizontal-based data process, we're going to look at one that's primarily used for display purposes only. And this is a process called surface normalization. This will be the first process we look at that uses GPS data. This is data that was collected with a GPS, and with the latitude and longitude, we also have elevation data. We can use that elevation data to topographically correct our file, which can help us interpret changes in material that may look deeper or shallow, but are really just a result of us going up or down a hill. You can use this process whether or not you had a GPS attached. If you collected data with a GPS attached, you will have in your waypoints table a latitude, a longitude, and an elevation. If you did not have a GPS attached, but you have elevation data, whether it's from GPS data collected after the fact or before, or you're taking local elevation changes with respect to some zero level, you can type in those elevations here at the appropriate scan number. So you can click and drag on your file to see what scan number corresponds to the distance that you have your elevation points in. You can type in a few of those down here, typing in different elevation data. And then after you apply that elevation data and save that into your data file, you can apply this surface normalization process to correct your file for elevation. So let's take a look at how to do that with an example file. I am first going to close the files we currently have open. You don't need to, but I usually do in between processes just to clean up the workspace. Again, you can do that by clicking the X next to the tabs. If you have a lot of tabs open, if you tried a lot of processes and you have some files open right now, a quick way to delete all of those or close all of those is to click on this G button in the top left-hand corner, and then select Close All Open Files. If you have any unsaved work in there, RADAN will probably ask if you want to save that file before closing it. Feel free to save or delete any of these files. And then once we have our clean workspace, we can open our new file and start processing it. So we're going to head back over to Home and click on Open. If you hover over Open, you'll notice that there is a keyboard command for it, Control-0 or Control-O. A lot of the common keyboard commands that you use in other Windows programs will work here, like Open and Save and Cut and Paste. So feel free to try using those if you're more comfortable using those keyboard commands. But I'm going to head over to Home and I'm going to click on Open. All right, and this time we're going to open a file called SurfaceNorm, short for Surface Normalization. All right. So I now have this file open. This is, again, a file collected with GPS data. I can confirm that by looking at the bottom bar of the screen here, where earlier we had the file name, the distance, the scan number, and the Z value, and now we have lat, long, and elevation. The elevation is in whatever your vertical scale is. So my elevation is in meters at this time. You can switch that at any time. If you're not much of a metric person, you can always head over to View and switch your vertical scale to whatever unit system you're more comfortable in. I'm going to keep it in the defaults. It doesn't really matter for this surface normalization. All right. So when I click on surface normalization, I'm going to see the pane over here on the left-hand side. I have those same 3 buttons, OK, cancel, and apply. And then down here, I have my parameters. Out of the 3 parameters, there's really only one we need to change, and that is the vertical scale. The vertical scale has 3 options, 1 to 1, 1 to 2, and 1 to 4. You will want to pick the vertical scale that allows all of your data to remain on the screen. So what do I mean by that? Well, 9 times out of 10, a vertical scale of 1 to 1 is not going to work for you if you have any elevation change at all. And that is because this keeps the vertical scale the same with respect to where it currently is. So that means this 10 meters of vertical space is all you're going to have to move up and down on. And that means if your file moves up by even a little bit or down by even a little bit, you might lose the top or bottom of the file. If it moves up or down at all, it's most likely going to move off the screen and will no longer be visible. So usually, if you have any elevation change, you're going to want your vertical scale to be set to at least 1 to 2. 1 to 2 doubles this vertical scale. So instead of going from 0 to, we'll say 11 or 12 meters, it goes from 0 to 20 to 24 meters, which means you have roughly 5 meters of play up and down, probably a little bit more than that, up and down, before the data might move off the screen and no longer be visible. That's going to be enough in this case here, but if you have a lot of elevation change, you can even quadruple it. That would give you 4 times the space here. So instead of 12 meters of play, you would have 48 meters of play, which would give you roughly 20 to 24 meters of space above and below the file, where the file can move around and still remain on the screen. So long story short, vertical scale is mainly all we need to change here. If you have a little bit of elevation change, 1 to 2 will do the trick. If you have a lot, 1 to 4 is the better option. If you are primarily going uphill or downhill, you can change the normal scale so that instead of moving up and down from 0, you can start it, 5 or 10 meters up, shifting your baseline up. If you're going downhill, you can move your normal level up. That'll give you a little bit more space to work with. If you are mainly moving uphill, you would want your normal level to be some negative value so that this is a little bit further down the screen than the middle, so that you have more room up here. So your normal level, you can shift accordingly if you're primarily going up or down, where again, if you're primarily going up, you would want this to be a negative number. If you're primarily going down, you'd want this to be a positive number. But in this case here, I usually just leave this set to 0. I play with the vertical scale so that my data stays on the screen, and then we hit OK. There is an apply button here. You can click it all you want, but nothing's going to happen. This is one of the few processes where the apply button doesn't really do anything. So in this case, we're just going to hit OK, cross our fingers, and see what happens. This green bar is going to fill as the process runs through the file. This is a particularly long file, so the process takes a little bit of time to run. And then once it's done, we will see our completed file here. So again, our normal level is set to 0, which means ground surface is smack dab in the middle of our vertical scale. And then it's going to move up and down according to the elevation. If we look at the previous file, we see that we have this, our unnormalized file, we have this layer that appears to get shallower as we move across. As we scroll through the file, we have some layers that are dipping, and then maybe they rise again further on. So we have some elevation changes. Could be layers that are actually getting deeper and more shallow, but if we look at the normalized file, we see that this layer was in fact fairly straight horizontally. We were just moving down a hill here. So we were moving down in elevation here, which was bringing us closer and closer to the layer. And then as we move across through the file, we see that we went over a little hill here, which gave us another horizontal layer, but it appears to get further away. And then we get closer to it deeper in the file. These are shifts that are actually getting deeper in depth as we move across. So these can be indicative of other features of interest. Again, we have another layer here that's getting further away as we go uphill, and then we get closer to it again as we go downhill. So for files like this, where we have a lot of elevation changes and we're moving up and down a lot, this can make interpreting our layers a lot more straightforward. So this would definitely be a great test case file for this particular process. You can see the top of the screen pretty clearly as the direct wave moves up and down, this consistent line here. The bottom of the file is a little bit harder to see in some places. It's this slightly darker line here. You can make it more pronounced by right-clicking and adding some display gain. Sometimes adding a little bit more display gain will make this bottom a little bit more pronounced. You can also do it by trying the more what's the right term for this? The color tables that are a little bit more colorful. Some of these, yeah, like this color table does a really good job of highlighting where the bottom of the file actually is. Yes, it's a little harder to see our layers because they're made up of many more colors, but the bottom of the actual data is a little bit clearer with this color table. So feel free to experiment with some of these other color tables here. While it might make interpreting the data itself a little harder, it is a pretty cool picture. And they do a good job of highlighting where the bottom of the actual file is, if that's something important for you. But overall, this process is very helpful if you're making interpretations with data that has a fair amount of elevation change. And you have that elevation change in your GPS data, or you collected it at some other moment and decided to apply it in the waypoints table. But overall, that's really it for this process, and that's really it for horizontal scale and distance-based processing. So three main processes here: horizontal scaling, distance normalization, and then surface normalization, primarily for display purposes here. So now we're going to move into how to edit data files using a very helpful process called edit block. So I'm going to close these two files here. Bringing us back to the main RADAN 7 screen. And then we're going to head back over to Home. Click on Open. And we're going to open that Strats file again. All right. So with Strats, we are looking at this same file that we looked at earlier with horizontal scaling. And now we're going to use a process called edit block. If you haven't yet changed your color table from the grayscale table to one of the other tables, this is the first process where I'd strongly suggest doing so. Because the tool that we're going to use here is really hard to see with the grayscale table. So if you really like grayscale, and I understand I like grayscale also, I would recommend trying color table 18, which is the one I'm currently using. It's the dirt color table. Very similar as far as what your negative and positive amplitudes are, but the color in the middle is brown, and the tool itself is going to be much easier to see. So we're going to head over to processing, and we're going to use this edit block process here. So when you click on edit block, a small block will show up on the file. It's this very narrow rectangle initially. I'm clicking on it and I'm dragging it to move it out in the middle. And as you move it out in the middle, you'll start to see these other boxes, 2 in the top corners, 1 on either side, and then there's also 1 at the very bottom. It can kind of be hard to make out that they're actually boxes, but just take my word for it. You have 6 boxes going around this file here, 1 on either side. There's actually 3 up top, but they're so close together it's hard to see, and then 3 at the bottom. So let's broaden this out and make it a little easier to see. I'm going to move my mouse to the very middle, and as I bring it closer, it'll turn from a normal cursor to a double arrowed cursor. Once you see it as a double arrow, you can click and drag on it to drag it further apart, highlighting a bigger area and allowing us to see the 1, 2, 3, 4, 5, 6, 7, 8 boxes we can grab and drag and move around. So we now have the edit block on the screen. So what can we do with this block? Well, if you look over on the side where the processing pane is, you'll see that there is a block operation, there is a start and end scan, and a start and end sample. This block, the units of this block are samples vertically and scan numbers horizontally. So this block is containing everything from scan 301 to scan 806. So 301 is over here on the left, 806 is over here on the right. And we're starting at sample 0, which is the very first sample at the top, and we're ending at sample 509, which is the second to last, third to last sample in this whole file. Remember from the earlier presentation where we talked about samples per scan? Samples are how we divide up each individual scan that we collect into a number of evenly spaced dots. And usually that number is 512 evenly spaced dots. This is software that was made by computer programmers, and if you know a little bit about programming, you might know that most of the time counting starts at 0 instead of 1. So the first sample is technically sample 0, which means the last sample would be sample 511 instead of 512. So here on the vertical scale, we're going from 0 to 511, and then here on the horizontal scale, we're starting at scan 301 and ending at scan 806. And in this block, we can choose to do one of 2 operations. This area that we're highlighting, we can either save it as its own file. So we can actually take this from the strats file, open it as its own file, and process just this one section. Or we can delete it. If this is a section of the file we did not intend to collect, or it's an area that we don't want to worry about processing, we can highlight it and delete it from the file. So these are 2 pretty powerful options that can be used in a variety of different ways. Maybe you have a 2-mile-long file and you're really only interested in this particular section of it. Maybe it's a 200-foot stretch that you want to process because you think there might be utilities, or you want to look for a layer analysis there, but you don't want to process all 2 miles. You can save this as its own file and process just that one section. Alternatively, maybe you collected a 2-mile-long file and there's a couple hundred feet that you didn't intend to collect. You can highlight that and delete it from the file so that you don't have to worry about processing it anymore. If you have GPS data associated with your GPR data, the GPS data will still be associated with the right locations. So you'll still have positioning for your file. You just won't have the GPR data on the screen anymore. Or alternatively, if you save it as its own file, that GPS data will be with it. So you can still position it using KML or KMZ after the fact once it's been processed. So again, a fairly straightforward process where we're just making a box and saving or deleting that from the file. That can be used in a variety of different ways. I'm going to show you one way to do it as well. There's an additional thing that you can do when it comes to editing files. And while we're going to use the edit block to do it, it uses some other function. So I'm just going to ask that you follow along with me here. And it'll make sense why we're doing this after the fact. The first thing that I want you to do is move the box all the way over to the left. And I want you to highlight or select the first 500 scans. So that means we're starting at scan 0 and we're ending at scan, if it's 500 scans, we're actually going to end at scan 499. Again, it's a little confusing, but we're starting counting at 0 instead of 1. So we're starting at 0 and 500 scans from there would be 499. Which then means for samples, we want to go from the bottom to the top. Sorry, from the top to the bottom. So we're starting at sample 0 and we're going to end at sample 511. You will notice that the box does not go all the way down to the bottom. That's okay. It's a display issue we've had for a while. As long as these numbers are correct, you don't have to worry about the particular size and shape of this box. These numbers are all that the process is using, so it's okay that it doesn't look right here. And we want to save this block. So as long as you have these numbers typed in correctly, again, disregard the appearance over here. We have these numbers typed in correctly, and then we will click OK. You'll have a new strats file at the top of the screen made up of the first 500 scans. Yours is probably strats p_2 or 3 or 4. Just take note of what that number is. Maybe write it down so that you know which file is made up of the first 500 scans. Once you have that written down, head back over to the strats file. So we're going to click on the strats tab to go back to that previous version, and we're going to head back to processing. We're going to head back to edit block, and then we're going to highlight the next 500 scans. So we are going to start at scan 500, and we're going to end at scan, we'll just say 1,000. So we're starting at scan 500 and we're ending at scan 1,000. Again, starting at sample 0, ending at sample 511, which means we're going the whole way up, disregarding the size of this, even though it's not correct. We're starting at scan 500, we're ending at scan 1,000, and we are going to save this as another file. So we're going to hit OK. It's going to give us a second strats file, this time made up of the next 500 scans. Take note of the name of the file and make sure that you know that that file is the second half of strats. Very important. So while we might be missing 30 or so scans, we've more or less split strats into 2 halves. So what I'm going to show you next is how to take other files and stitch them together into one file. You can actually take other files and you can append them together as long as they were collected with the same antenna at the same depth with the same number of samples per scan. So as long as the base values are all the same, samples, depth, and antenna frequency, you can append files together to create new files. Pretty cool. Maybe you have a really long stretch that you needed to collect and you only had a few minutes of battery left. Or maybe you weren't keeping an eye on your battery and it ran out halfway through the file. That's okay. You can, as long as you have that earlier half, you can collect the other half once you switch batteries and then append those two halves together into one file. In order to do this here, we can't have any data currently open. So just make sure that you know which half is which, and then we can close all of our currently open files. Again, you can do it by clicking on the X's. I like to just go up here and click on Close All Open Files. You should see RADAN 7 again. And then we're going to head up to the G. We're going to go down to Assemble Data File. And this time we're going to append files. So I'm going to select append files here. This first window, it's saying this is the folder. I'm going to look for the files you want to append together. This needs to be updated. We need to not browse in our source directory, but we need to browse where the processed files are saved. So this might be done in one of two ways. It depends on how you're automatically saving your files. If you have autosave files set to yes, and you're letting RADAN do the file saving automatically, then you can do precisely what I'm doing here. If you are not saving files automatically and you set up your own output directory, you are going to want to browse to your output directory. So it's not going to be in the location I'm going to show if you set up your own output directory. But if you let RADAN do it, then you should have in your GSSI sample data folder, you should have a folder here called PROC, P-R-O-C. Highlight that folder because that's where the two halves of strats are going to be, and then click OK. Again, if you do not have a proc folder, it's likely because you did not set up to save your files automatically, which means that you set up your own output directory. So make sure that you browse to that output directory instead of this proc folder. But if RADAN's never asked you, do you want to save or delete your files, then you're probably saving everything automatically, and you should just need to set the proc folder as your folder here. In the second bar, we need to specify what name we want to call this new file. So feel free to call this whatever you'd like. You can call it new strats. You can call it test file. You can call it my first file. I think I have a file in here called new strats already, so I'm just going to go for my first file. Just make sure not to include any special characters or periods in here, but everything else is fine. And then for this last step here, merge file databases, we do want to merge these into one long profile. You may not always want to do this, but in our case here, where we split a file in half, we're going to recreate it. So we do want to merge these into one long profile. And then we'll hit next. You should see a couple of files in here. You're not going to see all the files that I see, but you'll see a few files called strats. And you're likely going to want to pick the last two strats files. Remember which one is which. The first one you want to add is the first half of the strats file, and the second one you want to add is the second half. This order matters. This is the order that RADAN will stitch them together in. So make sure that the first half is first on the list and the second half is second. Once you have them ordered up, we can hit finish. And once you hit finish, you should see more or less a complete strats file here. Maybe minus a couple of scans at the end, but we've successfully recreated the strats file. All right, then. We're going to get into some new processes next. So please click on the X next to these tabs here. We're going to do quite a few processes now to this next file. And we're going to start to build out the processes that are performed most often in RADAN. There's a sequence of processes that are done most frequently in RADAN. A lot of these are one-off processes that you might use once or twice in specialized applications. But these next series of processes are ones that you're going to find yourself doing fairly regularly in RADAN. So let's head up to the G button here, the main button. We're going to open. You can also go to Home and Open. And we are going to open a file called Bandpass. Yeah, okay. So I'm going to close the tables pane to give us a little bit more space here. So you should just have processes over here on the left. You can also close processes. It'll open again when we open our first process. But we should have a file in front of us here. And this file looks a little nastier than some of the ones we've been looking at before. This file has a lot of interference in it. A lot of outside interference that we will need to address, that we will need to filter out to see the data that might be hidden behind it. A lot of these filters that we perform are usually done by default on the control unit, save for one or two of them. But if you're starting off with a file from scratch, then you're definitely going to need to do this process again. The processes I'm going to show you next to get your file to look as good as possible. This takes us back to our discussion of the ultra-wide band that we transmit into the ground. Keep that in mind. We'll touch on that after we discuss the first process we need to do here. So with this file open in front of us, we can take a look at the file header to see some history on this. This was collected in 2008 with a SUR 3000 control unit. With the SUR 3000 as well as the SUR 20, when we're collecting data on the control unit, so we discussed earlier the direct wave, right? That first wave that the receiver receives from the transmitter that's well understood and that we use to determine where ground surface is. The direct wave is this consistent line that we see at the top of the screen. And when we're collecting data in the field, the direct wave is automatically positioned at the top of the screen. So it's not something that we often need to address when we're in the field collecting data. But when we transfer files off of the control unit and we open it in RADAN, the direct wave needs to be repositioned. Again, this is only the case for the SUR 3000 and the SUR 20 and anything older than that. If you're using a current generation system like the Mini, the Utility Scan, the SUR 4000 or SUR 30, we retake care of the direct wave's position when you open it in our software. So this next process I'm going to show you is not something you need to do unless you're using a SUR 3000 or SUR 20. This process is called time zero. It's a process that we use to take care of ground surface and reposition it at the top of the screen. To do this process, we're going to head over to the processing pane, and you'll see all the way on the left, we have the time zero button. We're going to click on that. the processing pane is going to open up over here. We'll see a pane that's a little bit more complicated than the ones we've been working with before. We actually have something going on up here now. It might be a blue line with nothing else going on at the moment, but if you click and move your mouse around just a little bit in there, you'll see a red scan show up on the screen. So if you're using an older version of RADAN, this scope might already be filled out. It's a bug on the current version where you just need to move it a little bit to get it to reappear. So if you see that, or if you open it and you don't see a scan, it's something we're aware of, and we're going to address it on the next software update. So click and drag and move this around, and you should see your scope on the screen again. And what we can do here is we can click and drag and basically reposition where the 0.0 mark is, where ground surface is. Currently, the method of doing this is set to manual, where we would manually reposition ground surface. If you would rather have the computer do it, you can choose one of these automatic methods. We have auto peak, we have scan by scan, and we have a number of horizontal drift or horizontal threshold or horizontal mini tracking methods. I tested a few of these, and all 5 of these automatic methods will give you the same result. So I would recommend picking either manual or auto peak. I have been using auto peak more frequently now. It's quick, it's easy, it's fairly consistent. And if you want to give it a shot, you can select auto peak. It will automatically put ground surface in the right location. None of these other values are values we need to worry about. They all get set up when you manually move the scan around. It's mainly just the shift that we need to be concerned with. And that shift changes as you move the scan up and down. Whereas in the earlier processes, a lot of the action happened down here. For time 0, most of the action occurs up here. And as we make adjustments up here, these values will adjust accordingly. And it's really just this value. Auto peak does a good job. You can hit apply to see how it looks. If you like the way that it looks, and I do, I would hit OK, and that would run this process over the file and open a new bandpass file. All right. So we've taken care of time 0. We've put ground surface back at the top of the screen. And now we need to address the interference that we see. So I told you earlier that we were going to go back to one of the things that we discussed in our theory presentation, where we talked about what we transmit from these antennas. We're using a 400 megahertz antenna here. When we talk about our antennas, we tend to talk about them with one frequency, but it's a little misleading, because when we transmit not just one frequency, but an ultra wide band of frequencies with some upper and lower limit. Every time we transmit a scan, that scan is made up of a wide range of frequencies, and the receiver will attempt to receive reflections from that transmitted wave. The receiver is both really good at that and almost too good at that, because the receiver, left to its own devices, will receive anything in the microwave range that runs into it. And that could pose a problem, because there is a lot of other things transmitting in the microwave range that we might not be interested in seeing. We can see what happens when the receiver does not have limits set up to it by observing the file here on the screen. All of these vertical bands are outside frequencies, other transmitters that have been picked up by the receiver. Fortunately, we have methods at our disposal to filter this out. The processes that we use to filter these out are the FIR and IIR filters. There are 2 different families of filtering out these extraneous frequencies. At the end of the day, you can choose either one. You will get a very similar result no matter which one you choose, but I'm going to strongly suggest that you use the IIR filter instead of the FIR filter. So let's talk about what they mean, and then I'll discuss why the IIR is the preferred option. FIR is short for finite impulse response. It's called a finite impulse response filter, whereas IIR is short for infinite impulse response. The FIR and IIR filters were both developed and utilized at around the same time, and historically, the IIR filter was the one that was utilized more frequently. The IIR filter is electronically a much simpler filter to apply, so it can be applied a lot faster. And decades ago, with older computers, the time difference was very noticeable between the two. Nowadays, with our faster computers, you can use either one, and they can both be applied at the same time. They can both be applied in about the same amount of time. The benefit to the FIR filter historically is that the FIR filter is less likely to produce these phase shifts in your data. So what we're doing with these filters is we're actually going through the scan and we're removing frequencies outside of the range that we want to be concerned with, the ultra wide band that we're actually transmitting. And because we're changing the shape of the scan, we do run the risk of shifting targets around, the position of those targets around unexpectedly. Ultimately, they might move up or down by a sample or two, which is really not a dramatic change in depth. But it is still something to be concerned with. And the method by which these are performed in the FIR filter is a filter that has less of a likelihood of performing this phase shift. So it was seen as a safer filter to perform on your files. And that was true up until about a couple of years ago in RADAN. With the release of RADAN version 7.5, we changed the way that we perform our IIR filters. And this change made it so that this phase shift was no longer a thing we needed to be worried about. So IIR filters can now be performed on your radar data without worrying about shifting the depth of your targets. So that's good, right? That's a benefit. And in general, I would recommend doing just the IIR filter and not the IIR filter because this risk is no longer there. So getting into what the IIR filter settings are, when you click on IIR, you will see that, again, we have our scan and we have a much more complicated processing pane down below than we had with our earlier processes. They're split into two main sections, horizontal and vertical. What we're doing here is a vertical filter and a vertical filter only. So we only want to fill out the vertical parameters, of which there are 4: low pass, high pass, number of poles, and a filter mode. So let's start with low pass and high pass. So remember, we're talking about an ultra wide band that we're transmitting out of our antennas, centered at 400 megahertz, but with an upper and lower limit. The receiver, left to its own devices, will receive anything in the microwave range that runs into it, which is why we're seeing all of this additional interference on the screen. To filter out this interference, we can apply constraints to what the receiver is actually receiving. These constraints are what the low pass and high pass filters correspond to. Think of it as a fence that we put around the receiver, and we tell it, I only want you to receive things in this specific frequency range, and anything outside of the range, outside of the constraints that I set up, I don't want to see on the screen. I want to filter that out. It's a little confusing, but if you say it as a complete sentence, you'll be able to set it up properly. The low pass filter is the higher number, and the high pass filter is the lower number. The low pass filter allows anything lower than a specific frequency to pass through and show up on the screen. The high pass filter allows anything higher than a specific frequency to pass through and show up on the screen. For a 400 megahertz antenna, the extents of this are 800 and 100. So the low pass filter value is set to 800. And the high pass filter value set to 100. These are good starting points for a 400 megahertz antenna. So let's talk about how we found this number out. An easy way to calculate this number is to take the center frequency of your antenna. So that's the antenna frequency that we often use to denote what the antenna is, in this case, 400 megahertz. If you take that number, 400, and you multiply it by 2, that'll get you a good low pass starting point. And if you divide it by 4, that'll get you a good high pass starting point. So center frequency times 2 for your low pass filter, and center frequency divided by 4 for your high pass filter. So once we have these two values set, next we have what's called the number of poles. Number of poles is a new parameter in newer versions of RADAN, and it's a number that we use to make this filter stricter. So the higher this number is, the stricter these values are. By stricter, what I mean is, even though we're typing in 800 and 100, left to its default parameters with the number of poles set to 1, these numbers do allow for frequencies around this range to still show up on the screen. So even though we've typed in 800 and 100, it's still possible for frequencies slightly lower than 100 and slightly higher than 800 to show up on the screen. You can make these values stricter by increasing this number. You can bring it all the way up to 20. Usually I only bring it up to 12. You're not going to notice really much of a difference after that. But if you want to go full on, you can just bump the number of poles up to 20. But I found that setting it up to 12 is generally all you need. And then lastly, the filter mode, we're going to leave this set to pass. And I would say that, 99% of the time, that'll be the case for you as well. The IIR filter has the option of working as a band pass filter or a band stop filter. A band stop filter allows you to specify a specific frequency range that you want to filter out. So if I flip my filter mode from pass to stop, that means that I'm going to filter out everything between 800 and 100, effectively the entire scan, right? If I hit apply here, we only see the noise that we want to filter out. Right, definitely not what we're looking for in our case here. But this is primarily something that you would do with like a 100 megahertz antenna, a very low frequency that's right in the FM radio frequency range. If you're picking up a constant transmission from an FM radio station, you can specify your low pass and high pass filters for around that frequency range and stop it. You can actually filter that out. But in our case here, we want to pass through these frequencies. So I can hit apply to see how this looks. And already we have a huge improvement in our data quality. The vertical interference is gone. We still have some horizontal lines on the screen, but we're in much better shape than we were before. So I'll hit the OK button. This process will run across the file, and we'll have a new bandpass file on the screen. So the short and quick version of this is you have two different types of filters, FIR and IIR. IIR are the preferred filters. You take your center frequency, multiply it by 2 for your low pass, divide it by 4 for your high pass, set the number of poles to at least 12, make sure that the filter mode is set to pass, and click OK. And that will filter out any additional frequencies that you might have picked up with the receiver. Anything else in the microwave range close to the frequency range we operate under that might get picked up by the receiver. These filters are almost always applied by default, so you most likely have appropriate low pass and high pass filters for your antenna set up already on your system. But if you're starting with raw data, data that's had no filtering done to it, this is definitely something you're going to want to do at some point. Earlier in the day, when we looked at the first few processes like horizontal scaling and distance normalization, and I told you that when you apply these specific processes, we often get these strange display issues. So I'm actually just going to show it to you so that you can see it. Don't feel like you need to do what I'm about to do, but just follow along with me here so that what I'm going to explain will make more sense. So again, just watch what I'm doing here. If I click on home and open, and I open the Strats file that we looked at before, and in Strats, the first thing I showed you was horizontal scaling. I showed you the stretching operation, and we stretched it by 2 scans and hit OK. And after we hit OK, we have this really bright file on the screen. The easiest way to fix this is to head over to processing, head to that IIR filter we just looked at, and just apply an IIR filter. These filters, while powerful, are fairly safe to perform on your file multiple times. And yeah, after hitting apply or after hitting OK, after running this filter over the file, it now looks how it should have looked earlier. It's the original Strats stretched out, no longer super bright. So anytime you have a weird display issue after you run a process, like what we saw here and what we saw on a couple of the other processes, running a standard IIR high pass low pass filter can sometimes fix those display issues. Okay, so back to our regularly scheduled processing. We're over here at Bandpass, and we have done 2 processes to it so far. We've done a time zero correction, and we've done our low pass high pass filter. So next, we are going to get rid of the horizontal banding that we see on the screen. This is done, again, over at processing. This can be done with one of 2 filters. We can either get rid of this with the background removal filter, or we can get rid of this with the noise band removal filter. These filters will both do the same thing, but they do operate slightly differently. My preference leans towards using the noise band removal filter, but in this case here, we're going to get the same result no matter which one we do. But I'll explain the differences between them. So background removal is the most straightforward and I would say least aggressive horizontal banding filter. The way this filter works is you click on it. It's fairly straightforward. There's a background removal type of full pass, and while there are other options, full pass is the only one you'd want to use. And what this filter does is it goes through your file. It creates an average scan by observing every scan in your file. And after generating that average scan, it subtracts it from all of the scans in your file. What this process is intending to do is to locate and remove consistent horizontal lines on your screen. So anything that shows up at the same two-way travel time with the same strength of reflection throughout the entire scan, that should be removed with the background removal filter. This is a form of low frequency interference that we often see in high dielectric soils. So very wet, very conductive soils. Usually you'll get a lot of consistent horizontal banding on the screen. And we can get rid of that with this background removal filter. We can hit the apply button to see how it looks. Actually does a very good job and gets rid of really all of the noise that we had left. It gets rid of the direct wave at the top, which is usually what I try to get rid of. And we're also getting rid of the banding down below too, which is an added bonus. But anytime you have a file with a lot of consistent horizontal banding, the background removal filter is usually a good option. So background removal is a good process that's good for most of this banding removal. I'm going to hit cancel, and I'm going to show you what the noise band removal does. So the noise band removal is going to work very similarly to how background removal works. It just has an added bonus to it. This filter is precisely the same filter you might see on a Mini XT or on a utility scan. If you've used the band filter on either of those systems, the band filter is this noise band removal filter. So the band removal or noise band removal filter does just what the background removal filter does. It gets rid of consistent horizontal banding on the screen. But the bonus here is it has the ability to recognize where your hyperbolas are and skip over those regions, right? And that's a benefit to us because if one of these consistent lines cuts right through a hyperbola, a bumper arch, we're going to remove some of that amplitude. We're going to remove some of that signal strength, and that could weaken the hyperbolas that we see on the screen. Noise band removal has the ability of recognizing where those are. And if it sees that we're about to remove some amplitude from a hyperbolic feature, it simply skips over that region, keeping the strength of those hyperbolas intact and only getting rid of consistent banding on the screen from noise. You have 3 different algorithms to choose from: surface only, full scan, and a 100+ nanosecond band. We're going to use full scan band for this file. If you only want to remove the direct wave, that's what the surface only algorithm is for. And if you want to remove banding just from very, very deep features, deeper than 100 nanoseconds, that's what the 100+ nanosecond band is for. That algorithm was developed for the 200HS antenna, our newest low frequency antenna. But for here, we're going to do full scan band. And then I'm just going to hit the OK button to run that process over the file. Okay. And so now at this point, we've gone a pretty long way from where we were before. When we started with this bandpass file, we had a file that didn't have ground surface in the right spot and had a ton of vertical and horizontal lines hiding our deeper targets and features. We've now taken care of ground surface and filtered out those frequencies, showing us the data that was hidden behind, allowing us to analyze and make sense of our site much more clearly. Okay, so I have a couple of other things that I want to cover as we approach the end of day one. We've covered a fair amount of ground here in the processing pane so far. We took a look at some individual processes in the adjust scans area, like horizontal scaling, distance normalization, and edit block. We also took a look at surface normalization, and then we discussed some of the filters and time zero processes over here. Our high pass, low pass filters, and our background removal filters, as well as the optional dependent on control unit time zero process. So for this next file that we're going to open up and explore, we're going to use this as an opportunity to look at gain adjustments. So we're going to take a look at the different gain adjustments we have at our disposal, and then we'll wrap up with a discussion of migration. So with the files that you currently have open here, please make sure that you close them. We're not going to be using any of these Bandpass files for our next series of processes. So I'm going to click on this. I'm going to click on Close All Open Files. So that'll get us back to the main RADAN 7 screen here. You might have the processing pane open up on the side. And then we're going to head over to Home. We're going to click on Open. And we're going to open the Pit file, PIT. All right. So with the Pit file open, because this is a new file and we did not collect it, we can take a look at the file header to get a brief history on the file. Over here in the file header, we can see that this was collected in 2002. The system is unavailable, but we'll assume it was a SIR 3000 or SIR 20. It was also collected with what appears to be a 400 megahertz antenna. And if we scroll down, we see that there's been some processing done to it already. There's a range gain process done to it. That's one of the new ones we're going to talk about next. And there's also been an IIR filter with a low pass value of 800 and a high pass of 30. So that's a much lower high pass value than the one that we were using earlier. The file looks okay. We don't have any vertical interference like what we saw earlier, but we can apply this filter really as many times as we'd like without much issue. So it might be worth reapplying this to increase that high pass filter number to 100 instead of 30. Again, not really a requirement for this because we don't see any of that vertical interference, but for good measure and for practice, it might be worth doing anyway. But we do have something we need to take care of before we do that. If you look at the top of the screen, what you'll likely see is this consistent horizontal line here, and we want this to be, it's almost in the right location, but it's a little too far down for us. We actually want that up a little bit higher. So we are going to want to set our time zero in the correct location again. So we're going to head back over to processing. I'm actually going to close the file header as well because we don't really need it at this time. And then we're going to head over to processing, and we're going to start with our time zero process. So I'm going to click on time zero. As I said before, I like using the auto method, so I usually switch the method from manual to automatic. If you'd rather do it yourself, we're really just trying to position the very middle of that first positive pulse right here at the 0.0 mark. Auto peak does a pretty good job too. It's usually off by like a sampler or two, but in the grand scheme of things, that's not a huge change in depth. So Auto peak works fine, and then I'll hit OK. All right. So we have ground surface in the right position. Now that we've taken care of that, we can head back over to processing and try the IIR filter. So I'm going to click on IIR, and we're going to reapply our low pass and high pass. Low pass set to 800, high pass set to 100. And our number of poles, we're going to want to crank that up to 12. I'm just changing some of the other values just to see how it affects my scan shape up here. You generally don't really need, you're not going to see much of a difference when you toggle between them, but every so often I like to try different numbers of poles to see how I can change my waveform shape up here. I'm also going to try a slightly higher, yeah, that might actually be preferred in this case. So what am I looking at? What am I concerned with here? Ideally, when you set your low pass and high pass filter, you want to look at this scan, and ideally your scan is oscillating back and forth between this central line here. If the scan appears to wiggle back and forth and remain on one side of the line, which is what I see up here, I see that it bounces back a little bit, but it doesn't quite cross this line before going out again, and then it goes over here, it bounces back, and then slightly forward, and then back again over here. This is something that, while not huge and not that consequential to our ability to interpret, if I can, I would want this to go all the way back across the central line first before heading out again. Ideally, this moves back and forth across the center line and doesn't do any of these wiggles while remaining on one side. We can also see a little bit of it down here as well, where it bounces over, it bounces back, and it doesn't quite cross this line before coming out again. Again, these are small reflections here and there, and ultimately our scan appears to be maintaining a bounce back and forth across this central line, but there are some cases where that's not the case. Ways that we can fix this, if you see anything like this, usually that means that you need to specify a higher high pass value. Keeping in mind that your center frequency is 400 megahertz. So we can get closer than 100, but we don't want to get too close to 400. Usually I try to make sure that this value for a 400 megahertz antenna, and for any antenna regardless, I want to try to stay at least 200 megahertz away from the center frequency. So for the 400 megahertz antenna, that means I don't want to go any higher than 200. And for the low pass filter, I don't want to go any lower than 600. I try to give myself a good 400 megahertz around the center frequency where I'm not really making any adjustments. But we do have some wiggle room here, so I tried a value of 150, and I find that I like that it fixed this up here. It still looks a little strange over here, and it's still not quite crossing the central line here, so we can try going a little higher. It looks a little better. It's almost crossing that central threshold there. And with 200 actually looks really good. So that is probably as good as we're going to get. I wouldn't want to go much higher than that. It's not quite perfect up here, but it does look a lot better, especially down here, than it did beforehand. So I'm going to say that a high pass value of 200. Yeah, and our data for the most part is still intact. It actually looks a lot better up here. You see how it's kind of shaded in the positive beforehand, and then when I hit the apply button, that positive shading goes away. That's a good sign. That means we're oscillating more so over the central line than we are, staying over on the right or left-hand side. So this higher high pass filter value, I think is going to help us out a lot. Again, overall, not really a huge impact in the image. So if you miss this step, it shouldn't affect your analysis overall. This is just me being picky about the appearance of the scope, but this looks good to me. I'm thinking a low pass of 800 and a high pass of 200, and then the number of poles set to 12 should give us a good result. So I'll hit the OK button. And there we have our frequency filtered file. So we've taken care of time zero. We've filtered our frequencies a little bit more so. And the only other process that we showed earlier that we haven't done here yet is background removal. So let's give that a shot. We're going to head over to processing. We have two options, background or noise band. I'm a big fan of noise band, so I'm going to give that a shot first. Sometimes with noise band removal, it does make these other bands show up. I'm not seeing that in this case, which is a good sign. So I think I'm going to move forward with noise band removal. Cool. Cleaned up the top pretty nicely. There wasn't really much else in terms of banding. It was really just the top of the screen, and that's now filtered out. So we have a pretty good looking file at this point. If you are using a different color table and different color transform, as a reminder, I'm using color table 18, which is the dirt color table. Works pretty well. And I'm using color Xform 4 in this case, which does make the bottom of the image very strong and very pronounced. I am going to actually move this up to LM12 because this is soils data, and ultimately, while I want my targets to be bright and easy to see, I might not want them to be that bright. So you can honestly stick with either color Xform because we're going to make changes anyway, but I'm moving my color Xform up to 12 instead of the LM4 Xform that I was at before. Okay, so we filtered out some noise. We've taken care of time zero, and now we're going to move into some new stuff. So when you look at this file, it should be pretty clear that the top half of the screen is not nearly as bright as the bottom half of the screen. It doesn't matter which color transform you use, the top is always going to be much fainter than the bottom, which means we have good screen contrast set for the bottom, but we want more screen contrast on the top half of the screen. This is a time variable gain curve that we need to make an adjustment to. And there are two ways that we can go about doing this. If you look at the file header, you'll see that there has already been some range gain applied to this file. A range gain curve, a time variable gain curve, made up of 5 points, and we can see the gain applied at each point. Basically, this means we have 5 evenly spaced dots going down each file. Dot 1 is at the very top, dot 5 is at the very bottom, and the other 3 are spaced evenly in between, which means right in the middle of the file, we have a gain point set to 40 decibels. And then we'll say 3/4 of the way down the screen, we have 57 decibels. 1/4 of the way, we have 16 decibels. And then we have 5 at the top and 57 at the bottom. A time variable gain curve, which is set okay, but I don't think it's set well enough for this file because we want more contrast here and maybe even a little bit less here. So again, two ways of going about that. We can either, in processing, apply another one over top by clicking range gain and applying another range gain curve on top of this one, or we can try gain restoration first, which removes the screen contrast already on this file, and then apply a range gain to the file with no gain on it. In practice, option 2 is the preferred option. It'll get you a better result, in my opinion, and it will make a curve that is more what you would expect, a curve where we have more contrast the deeper we go. If we try applying a curve on top of the one that already exists, we're going to end up applying more contrast at the top and actually removing some contrast at the bottom, which is a very uncommon range gain curve. It'll still work just fine, but I think for this file in practice, what I've seen is gain restoration is usually better, and then a range gain afterwards. So this is the method we're going to do today. We're going to click on gain restoration. Nothing we need to change here. Just click on the process and then click OK. It's going to get rid of the time variable gain. It's going to make the file look pretty bad, right? You're going to think, oh, I've been following along and everything's been better, and this is the first process that's actually made the file look terrible. But that's okay. We've gotten rid of the time variable gain, and now we're going to apply it from scratch, and it'll get us a much better looking file once we're done. So we've gotten rid of the time variable gain, and now we're ready to head to range gain. So I'm going to click on range gain. There are a few different gain types: automatic, exponential, linear, and smart. I would recommend the exponential gain type anytime you do this. This is the most straightforward way to apply your gain. It's going to give you the most control over your points, and it should get you a really good result once it's been set. You can have this do it automatically as well. I think the auto gain works okay, but I like doing this manually. I think it'll get you a better result if you do it this way. So we're going to pick the exponential gain type. And now we have the option of changing how many points we're using. Dependent on your control unit, you can usually do up to 8 points. In RADAN, you can do up to 16. That's 16 evenly spaced dots that you can control. 16 is generally overkill in my opinion. I usually don't do any more than 10. In practice, I don't really have any science behind this. I just press the up arrow until I feel like there are enough points on the screen. Usually that number is somewhere between 7 and 10. In this case, I'm going to stop it at 9. 9 seems to be pretty good. I have a good amount of points here. If you find that there's an area you want to add adjustments to and you just don't have a point in that location, you can add or remove points until the dots are where you want them to be, and then that should be the number you stick with. No real calculations that you really need to do for this. Just add enough points so that you have enough control over it to make a fairly good representative curve. And in practice, I found that number is usually somewhere between 7 and 10. Okay, so we have 9 evenly spaced points, and they're all currently set to 0. So to start making adjustments to them, I'm going to start with a point in the middle so that you see how this works. But usually I start at the top and I just work my way down. So I'm going to start right here at 50 nanoseconds down the screen. And if you look up here, you'll see that there are some black dots going down the middle. Over on the left, it goes to -5, and over on the right, it goes to +5. I'm going to drag this point. I'm going to click and drag this point way far to the right. And as you drag it to the right, you're not going to see anything change. But as soon as you let go, if you could pay careful attention to the top of the screen, once I let go, I see that I can now go not from 0 to 5, but from 0 to 10. And if I do that again, I can now go to 20 and 40 and 50 and 100. And now we're starting to see some changes. If I hit the apply button here, we'll see that I have a ton of screen contrast right in the middle of the file and no real contrast anywhere else. So we've now added a ton of gain to the middle of the file and gain nowhere else, which is obviously not what we're looking for. This also works the opposite way. If I drag it over to the left, I will make it weaker. So you're going to make the scan look fainter if you drag it to the left. If you're starting with a scan like this where there's nothing really going on, you're probably not going to drag any of your points to the left, but that is what the left is for. So in practice, you're going to start at 0 everywhere. And I usually just change the first couple of points and hit apply. This is not a process where you'd want to adjust every point and then hit apply and see how good you did. This is definitely one where you want to do a couple at a time. It's going to take some time to work your way down the scan. But over time, if you do them just 1 or 2 at a time, you'll be able to make adjustments and fix them and know where in the scan this is taking place at. Because it's hard to position these on the screen. You can get I know this is halfway down because it ends at 100 and this is at 50, but everywhere else I'm just sort of guessing. This is going to seem a little counterintuitive, but the first point, it's usually best if you drag it off to the left, especially if you're starting with a raw scan. And then the second point, you can drag it a little bit to the right. And then the third one, even further to the right. And then you're just going to trend right as you go deeper. Usually the first point, you want to add a little bit of negative gain, and then you trend positive the rest of the way down. It's mainly just because of where the points are positioned in the file. But I found that that gets me the best result most of the time. And usually I want to drag these out until I start to see some contrast. And if I hit apply and I see some good contrast up here, that means I'm on the right track. So again, a couple of points at a time. This is going to take a little bit of time to get set right, but the results will be worthwhile. As we drag our points over, we're getting a way easier to look at image. So I encourage you to give this a shot, trying it just a couple of points at a time. And then once you have a good idea of where you are and what you're looking for, what your constraints are, you can afford to do, maybe a couple of more points here and there. But for the most part, we should just be trending to the right as we go deeper, where ideally everything looks to be about the same strength. You know what? That looks pretty good to me. So we're just going to work our way down the scan. You're going to make adjustments to 1 or 2 points at most, and then hit the apply button, see how you did, hit reset, make some adjustments, hit apply, hit reset, make some adjustments, and then once you're happy with how it looks, work your way down to the next point or so. Usually I do 2 points at a time. For the first The first time I do this, I usually do the first 3 points, and then I do 2, 2, 2 until I'm at the bottom. If 2 is too much, you can just do 1 point at a time. That's fine too. It's just important that as you're working your way down, you're eventually going to have a scan that looks roughly the same screen contrast wise from top to bottom. Okay. So once you're happy with the way that your curve is set, we can hit the OK button, and this process will run on your file. So range gain is a very helpful process. It's something that's almost always done by default on your scan while you're collecting it. And it's definitely something you're going to want to do if you start with raw data without any processes done to it. You're almost always going to need some form of range gain to see the data that you had collected. Range gain is one way to go about this. If you look at the processing pane, you'll see that there is a third gain option. And the third option is adaptive gain. Adaptive gain is a process that might be familiar to you if you have our wireless utility scan system. It's precisely the gain algorithm that we use there. What adaptive gain does is it sets a curve of 5 points on your file, and the amount of gain that we apply at each point adapts or changes as it moves horizontally through your file. Instead of applying a static curve, which is what we do here, where we apply the same amount of screen contrast in the same places moving down the file, we apply an adaptive curve made up of the same number of points, but with values that change as it moves horizontally through your file. This can be beneficial if you are applying range gain to a file that was collected over multiple environments, over multiple soil types. Maybe you collected a file that went from a grassy area to pavement to concrete, and the screen contrast that you need in each one is going to be different. It's going to be noticeably different. You could use edit block, save those chunks of the file as their own file and process them individually, or you can try an adaptive gain and apply adaptive gain to your file. And that should make it so that all of your targets appear with roughly the same signal strength, even though the environments themselves are different. To view how this looks, I'm going to go to the previous instance of Pit, which is the Pit file that was after gain restoration, the one that's really muted and hard to see. And then I'm going to head over to processing. I'm going to click on adaptive gain. You have 3 algorithms: slow, normal, or fast. I am a fan of normal. You're not really going to see much of a difference between the 3. And I figured normal's pretty normal, middle of the road. So we'll start with the normal adaptation. And then I'll hit OK. And we'll find that it does a fairly good job. It looks pretty bright, pretty easy to see. Comparatively, I think our range gain curve did a better job at keeping everything with the same strength, but adaptive gain certainly made it so that everything was visible. Our deeper targets are a little brighter. Our shallower targets are a little fainter, but all of it, for the most part, is visible. So if you're in a time crunch and you want to process your data quickly, adaptive gain is a good call. If you have collected data in multiple environments, adaptive gain can also be a good option for you. I think in practice, range gain will often get you the better result, especially if the environment is roughly in the same soil or soil type. But for quick and fast processing, adaptive gain is a good one. So Different ways of adjusting screen contrast, but I would say that one of them at the very least would be necessary. One of the two would be necessary if you were starting with raw data. There is one additional process I wanted to show you today, and that process is migration. So migration is the last process that we would want to do on this file. Perhaps not in this specific instance, but depending on what our goal was and what we were going to do with this file after the fact, we may or may not want to perform a migration. So I'm not going to use the adaptive gain file for this. I'm just going to close this out, and I'm going to use the range gain file for this. You can use whichever one you'd like. The only thing that's really important is that, one, you're using a non-gray table. This is another process that uses a tool, and the tool is going to be hard to see if you're using the grayscale table. So if you're a fan of grayscale, try 18 out. And two, you're going to need to see some hyperbolas on the screen, which we have plenty of here. So let's talk about what this process does. The migration process is a process that you can use to fit over a hyperbola that you see on the screen. The migration process is a process that puts a tool on the screen that you can use to fit to a hyperbola. Much like what the set dielectric tool does or what show hyperbola does on the Surf 4000 or utility scan or XT systems, this hyperbola tool you use to fit over a real one that you see on the screen. And as you adjust the shape of the hyperbola, you're changing the dielectric constant of the file. So migration is a process that you can use to calibrate your dielectric constant to get a better sense of the radar wave speed and therefore how deep your targets are. So in that regard, the migration process does something similar to what our other control units do, but this process takes it just one step further. Not only do we use this to determine our dielectric constant, but we also attempt to collapse the tails of our hyperbolas into individual dots. So when we actually run this process over our file, the tails are going to attempt to focus into a single point. This might not be beneficial if we're just looking at data in 2D, which is what our case is here. But if our intention is to eventually look at our targets in 3D, which is what we're going to be doing a lot of tomorrow, then migration will help make these targets pop much more easily. They're going to be a lot easier to see, and they're going to be a lot easier to distinguish if we migrate or perform a migration process prior to looking at it in 3D. So we're not going to take it into the 3D view, but we will at least explore how the migration process works today. Okay, so let's talk about this process. I'm going to click on the migration process. It's going to bring a tool up on the screen. So I have my tool over here. I'm just going to move it off on the screen so that you can see what the tool does. This tool is made up of 3 boxes. I can click and drag on these boxes to change the shape of this hyperbola on the screen. The ultimate goal of this process is to try to build a hyperbola that represents a real one that I see on the screen here. In practice, it would be best to do this on the deepest target that you can see in a file. The deeper the target is, the more representative, the better the average of your dielectric constant will be. Right, soils are pretty inconsistent, so the deeper down we migrate off of, the better the constant we end up with will average the soil that we've traveled through down to that depth. So if you have multiple targets to choose from and you're really only concerned with targets at a specific depth, you would be best off migrating down to that depth at the very least. But in our case here, where we're really just doing this to practice and not really for any other goal, then we can migrate off of any hyperbola that we can see easily. So I'm just going to pick this one here. This bright one down here that I can see the whole tails of and I can see the arch shape of. So there are a lot of things going on in this processing pane here. There's a velocity plot, which we haven't seen yet, and there's also a bunch of other numbers down here. Fortunately, there is only one number and one number only we need to be concerned with, and that is this number here, the dielectric constant. All these other values are going to change when we start making changes to the shape and these other lines and things. So the only one that we really need to keep an eye on is this number here, the dielectric constant. So I'm going to bring this over here. I'm going to try to fit this as best as I can. And I would say that looks pretty good to me. Maybe a little higher. There's going to be a pretty wide range that looks okay, and this looks okay to me. So I think I'm fitting the arch shape pretty well with this dielectric. So I think I have the arch shape fit, and now I need to change these vertical bars at the top. So these vertical bars here, whereas this gives me the arch shape, these vertical bars are supposed to correspond with the arch width. They should be roughly at the edges of the visible tails of the hyperbola. So once the tails are no longer visible, that's roughly where these vertical lines should contain. Do not pull your hair out setting these vertical bars up. It doesn't need to be exactly at the edges of the tails. As long as you're pretty close, this process works well. So they don't need to be exactly at the edges of the visible tails. Just get it as close as you can. So I think that looks pretty good to me. I have the arch shape fit well. I think these vertical bars are far enough to at least contain my whole hyperbola. Just don't forget about them. If you leave them really, really close together, you're going to have a really hard time getting the migration to look nice. So just make sure you pull them, at least, you know, this number should be a little over a 150. And then hit the apply button and see how it looks. When you hit the apply button, you're going to see that your file looks a lot different. What is the goal of this process? The goal of this process is to collapse your hyperbola into as perfect of a dot as we can get. And for all intents and purposes, for the one that I wanted to fit, we did a very good job. This dot is precisely what we were looking for. There are some imperfections elsewhere, but the dot that we were trying to fit off of got focused very well. If we look elsewhere in the file, or rather, if I just stay focused on here, let me show you what it looks like when it's not set up right. So let's say I did a poor job. Let's say I think that this fit my hyperbola well. Dielectric of 5.9, and I hit apply. If you hit the apply button and everything flips, the tails no longer point down, but they point up instead, this means the dielectric constant is too low and it needs to go up in the direction the tails are pointing. you might see where I'm getting at with this. If the tails point up when my dielectric is too low, if my dielectric is too high and I hit apply, the tails will still point down. So this is telling me that my dielectric is too high and it needs to go down in the direction the tails point. So after hitting the apply button, whatever direction your tails are pointing, that's the direction this number needs to move. If they point down, this needs to go down. If they point up, it needs to go up. In our case here, 24.23 is too high, needs to go down. You can either, at this point, you can either bring the hyperbola over and change the shape, or you can just type in a new number here. Usually that's what I do. I fit it with this tool in the beginning, and then once I know what I need to do, once I know where to make the adjustments, I just go over here and I type in different numbers. So I hit reset first to reset my view, and then 24 is too high, so let me go down to 20. Usually I only go down 1 or maybe even half a value at a time, but I know I'm really far away here, so I went down by 4. And then hit apply. Close, but not quite. So let's try 19. Apply. Getting closer. 18. Apply. Reset. Closer. Apply. Reset. 16. Apply. Pretty close. Just a little bit down. And then hit reset. So at this point, I might try, 15.5 or, 15. But that looks pretty good to me. So maybe a little lower. I'll try 15. Yeah. So once you think you have it fit well, we can hit the OK button to run this migration across the whole file. Now, there is one number that I sometimes mess around with once I have my dielectric set accurately, and that's the gain. This number can be higher or lower to make the scan brighter after you do this. The default is 4, and 4 generally does okay, but the higher this number is, the brighter the file will be after this migration has been conducted. And migration usually makes the file look noticeably fainter. So it might be beneficial to just increase this number, right? And see how it looks a little bit brighter up here than it did before. The default set to 4 kept everything pretty faint up top. By bumping this value up to 8, just doubled it. You can even go up to 10. 10's probably fine too. It'll just make the scan look, right, just really see what it does. It just makes the scan brighter after this migration's run. The same effect can be achieved just by adding some display gain once you do this process. This is just another way to do it. So if you forget this, it's fine. It's fixable with other things, mainly just display gain. But this is another way to do it. And sometimes I like to do this. So I'll hit the OK button. This process will run across the file. And now we have a migrated file. The main benefit here for this, where we are only really looking at one 2D file, is that after we do this migration, we have a better sense of our dielectric constant, which gives us a better accuracy for our target depths. So that's the primary goal here. If you want to obtain that data, basically you want the more accurate constant, but you don't want the whole migration where you're focusing your hyperbolas, you can just remember what that number is, and then head back to the previous version of the file over here, and just type in that new number. Usually the number updates automatically when you're doing the migration on it, but if for some reason this number is not the number that you had after you did your migration, you can go over here at any time and just type in what that number is. And the dielectric constant will update accordingly. So we've covered a lot of ground in the processing pane. We've talked about a good number of the processes here, which will definitely prepare us for the grids that we're going to take a look at tomorrow. We're going to be doing a lot of these processes in great detail over the course of the day tomorrow. So we'll definitely be revisiting time zero. We'll be revisiting IAR and FIR. We'll be revisiting, background, migration, range gain over the course of our 3D grid analysis tomorrow. So we'll definitely have plenty of time to practice these then. I have a couple of other processes that I think we'll touch on tomorrow as well. But for now, I think we've covered all that I intended to cover for today.